first, let's talk about functions.
Hold on just a minute. You thought you were going to get away without taking notes throughout this video. Lucky for you, we've built in a feature into this video where any time where you need to take notes, we have actually set a notes emoji in the top right corner of the screen to notify you of when you should take notes and when you should just pay attention to the video. So feel free to look at that top right corner to the screen to know if you should be taking notes or not.
At a high level, functions are binary relations between two sets of values. Think of them as a box with two holes. When you feed the box a value, it will modify that value in some way and then spit out the result, like finding a y value by substituting for x. The beauty of functions is all values are modified in the same way. Here's an example. Say you have the function of f of x equals x plus 1. That essentially states that whatever rule you plug into the function, substituting for x, the output will always be the input plus 1. If we substitute x for 1, the output will be 2. If we substitute x for 10, the output would be 11. One of the most common terms you will hear are preimage and image. At its core, these are just fancy mathematical terms for input and output, or x and y.
Two other important terms are the domain and range. Even though they sound complex, they represent fairly simple concepts. Let's start with the domain. The domain is the set of numbers that can input into a specific function, restricting what the x can be. The range, on the other hand, is all the values that a specific function can take on, restricting what the y can be. Functions are what map a value in the domain to a value in the range. Let's look at the function and see how this would play out. F of x equals 3x plus 8. Plug an 8 and 9 into the function. Let's think about this. We're inputting the number 8 and the function outputs a 32. Again, we're plugging a 9 and the function outputs 35. Therefore, the domain of the function includes 8 and 9. The range includes 32 and 35. What the function is doing is mapping us from that 8 to 32 and that 9 to 35.
There is one other important term beyond just domain and range which we need to understand and know. It's called codomain, and it is incredibly similar to range, however it's not exactly the same. Now when explaining it, I like to think of students taking tests. So let's say you have student A, student B, student C, student D. In this case, we're just going to represent those numbers, student 1, student 2, student 3, and student 4. Now this is the domain. These are the x values, the inputs, the preimages, the people who are taking the tests. Now the codomain is every single grade these students could get. So since it is a test from 0 to 100, these students can get an image or a y value between 0 to 100. Those are all of the possible y values. However, these four students, got the grades 100, 89, 21, and 35. So only 100, 89, 21, and 35 are the range. However, 0 to 100, all of those different numbers, that is the codomain. So essentially, in mathematical terms, the codomain is every single image that a function can give, every single y value, every single value a function can take on. However, the range only refers to the images with corresponding preimages.
Well, you might think, is there a way I could take the 32 and map it into the 8? There is some functions that could take the range and map into the domain, almost like an inverse. Lucky for us, they are. They are called inverse functions. In this case, we call it the inverse of f using the notation of f to the negative 1 of x. So how would you solve this? First thing we'll do is reformat the function of x, f of x equals 3x plus 8 to y equals 3x plus 8. Then it's simple as solving for x. First you subtract 8 on both sides, then divide both sides by 3. But why does this work? All we need to do is look at the equations for that. A standard function is a function of x that gives us a y. In other words, a function of all values of values the domain that gives us the corresponding value of the range. An inverse function is the opposite, a function of y that gives us an x. In other words, a function of values of the range that give us the corresponding value of the domain.
Now let's talk about composite functions. Now up to this point we know we can plug in numbers into functions. For example, the function f of x equals x plus 3. We can plug in numbers as x. However, what if we could plug in functions as x? Literally substituting x with other functions. To help you visualize and conceptualize this a little better, let's take the two functions f of x and g of x. Literally, what we're doing with composite functions is taking the whole g of x and plugging it in as x in another function, in this case f. Composite functions, or compositions, the way that I like to think of it, it's when we're inputting the value of one function into another function, kind of like nesting them. So how do they look, what do they mean, and how do you call them? So let's start with how do they look. You have the function f of x and you have the function g of x, for example. Then this is how a composite function of f of g of x would look, and that's how you'd call it, f of g of x. If it has three composed functions, you'd say f of g of h of x, for example. And what this means is that you're plugging in the value of g of x as the x for f, as a preimage for f.
The thing about composite functions is that they can be simple or complex. Simple composite functions, for example, have two composed functions, f of j or of x. More complex functions can be nested, and there can be really an infinite amount of them. So for example, there can be a really complex composite function called f of j, of g, of t, of s, of o, of x, so on and so forth. So let's look at two examples. Let's first look at the functions that are given to us. In this case, it is f of x equals x squared minus 22, g of x equals 2 to the x plus 10, h of x equals x plus 10, and j of x equals x over 2. And then they're asking us to solve for h of g of 3. So again, we want to start from the center or middle out. So we'd first solve for g of 3, which is the same as saying 2 to the 3 plus 10, which is the same as saying 8 plus 10, which is 18. So g of 3 is 18. And then if we plug that value of g of 3 into the function h of x, so h of g of 3 is the same as saying h of 18, which is the same as saying 18 plus 10, which is the same as saying, which is equal to 28. So in other words, h of g of 3 is equal to 28. Let's look at another example. So we're going to be using the same functions, and in this case, they're asking us to solve for j of g of f of 5. So again, we start on the middle out. We solve for f of 5, which is the same as 5 squared minus 22, which is 25 minus 22, which is 3. Then we plug the value of f of 5, which is 3, to g of f of 5, which would be g of 3, which is 2 to the third power plus 10, which is 8 plus 10, which is 18. And then we plug that value into the j function. So it would be j of g of f of 5, which is the same as saying j of 18 And then that's going to give us a value of 9. So therefore, j of g of f of 5 is equal to 9. One other thing they might ask you is to simplify composite functions. So in this case, we have to look at the composite functions given to us. H of x equals x minus 3 and g of x equals negative 3x plus 2. So what if they ask us to simplify g of h of x? So basically what you're doing is implementing and really inputting the value of h of x into g of x with the x. So therefore it would be negative 3 times x minus 3, all within parentheses, plus 2. And you have to remember to distribute the negative 3, not the 3. So you'd be left with negative 3x plus 9 plus 2, which you can then combine like terms and be left with negative 3x plus 11, which would be the most simplified version of g of h of x.
So the final thing I want to touch on regarding composed functions is what I like to call inverse composed functions. So when I was looking into composed functions, I realized that there might be a very interesting pattern. Since inverse functions and functions are respectively opposite, what happens if you compose them? Well, we're about to find out. Let's take the example function f of x equals 2x minus 7. Now let's simply convert that function into an inverse of itself. So first we're going to set it to y equals 2x minus 7. We're then going to switch y and x, add 7 on both sides. We're going to be left with x plus 7 equals 2y, and then divide both sides by 2 to get rid of the 2. And we're going to be left with y equals x plus 7 over 2, and that is the respective inverse of 2x plus 7. So in theory, this is how the composite function would actually look. Now it is definitely a mouthful, so let's give it a try. F of negative 1 of f of x. Yeah, that's it. So let's go ahead and solve f to the negative 1 of f of 2, where x in this case would be 2. So first, we'd use exactly the same rules as any other composite function. We go from the middle out. So f of 2 is the same as saying 2 times 2 minus 7, which is 4 minus 7, which is equal to negative 3. And then we can plug that negative 3 as the input to the f to the negative 1 of x. So f to the negative 1 of 3 is the same as saying negative 3 plus 7 over 2, which is equal to 4 over 2, which is equal to 2. That's interesting. F to the negative 1 of f of 2 is equal to 2. Now let's analyze that and record our observations. So here is the analysis of inverse composite functions. There is two key takeaways that we should be focusing on here. The first one is that if the number of composed functions, by composed functions inside a composite function, I basically mean, for example, if it's f of g of h of x, that would be 3 composed functions where it's f, g, and h. If it is f of j of x, then there would be 2 composed functions. So if the total of composed functions is even, the output will be the value of x. So let's think about this. If the total amount of composed functions is even, so if we have something like f to the negative 1 of f to the negative 1 of f of x, then the value of x will be the same as the value of the output of that composite function. Then the second key takeaway here is that if the number of composed functions is odd, the output will be the value of f of x, not x, but f of x. So essentially, if we have something like, for example, f to the negative 1 of f to the negative 1 of x, the value of that composite function will be f of x. So this is the algorithm. It's written in TypeScript, and essentially it is actually a computer science function, and it's doing a ton of computational logic here. essentially it is analyzing this composite function right here. So in this case, the composite function is h of g of f of j of x. And then it's going to actually analyze that and give us all of the information of that composite function. So let's go ahead and run the program. And here we go. So the first thing that we're going to be greeted with is going to be original composite function. So it's going to tell us the original composite function, what that was. Then it's going to tell us the number of composed functions. So as you can see here, there are four. There is h of x, g of x, f of x, and j of x. And then it's actually going to tell us how to solve in 4 steps. As I explained before in the video, from the middle out. So the first thing that we're going to do is solve for j of x. Then we're going to plug the value of j of x into here and solve for f of j of x. The third step is to plug the value of f of j of x to g of x to solve for g of f of j of x. And then finally, plug the value of g of f of j of x to h of x, solving for h of g of f of j of x. It is a wordful. And the beauty of this is that it works with however big of a composite function or however small of a composite function. So you can have, for example, h of j of x, and it will solve. You can see here, it's just going to say original composite function of h of j of x, 2 composed functions, the composed function, then the composed functions, and then the steps to solve. And then you can literally go crazy. You can say h of j of k of m of l of o of p, for example, of x. Let's see what happens there. 7 composed functions, all of the composed functions and all of the steps to solve. And I could keep on doing that. So that's the algorithm right there. If you want to check out the code, it's right here. And it's also in my GitHub repository. So if you go to markmusic2727, GitHub/markmusic2727, go to repositories, you go to composite me, we're going to be able to see the code right here.